Good morning, Applied Physics students. Here is your teaching video for the Concept Development Practice page 32-2. Again, this chapter is about electrostatics. And so remember, we're talking about charge. We are talking about Coulomb's law. And so this CDP is looking at how different ways that we can charge things. So, to begin with, we see the outer electrons in metals are not tightly bound to the atomic nuclei. They are free to roam in the material. Such materials are good, and they're good conductors. So when the electrons are free to move, that makes the substance a good conductor. So the reason that metals are such good conductors is because those electrons are free to move in them, which means that they'll conduct electricity. They also conduct heat. Electrons in other materials are tightly bound to the atomic nuclei and are not free to roam in the material. These materials are good because those electrons can't move. That makes them good insulators. So if electrons are free to move, we have a conductor. If electrons are not free to move, we have an insulator. So now we're kind of looking at a way to charge something. So a rubber rod that has been rubbed with fur is negatively charged because rubber holds electrons better than fur does. When the rod touches a metal sphere, some of the charge from the rod spreads onto the metal sphere because like charges repel one another. So what it's saying here is because all of these electrons are on this tiny little rod and they don't like to be near each other, they're going to try to spread out. When the rod is removed, the charge spreads evenly over the metal sphere and remains there because the insulating stand prevents its flow to the ground. The negatively charged rod has given the sphere a negative charge. This is charging by contact and is shown to the right. So it's contact because the rod is actually touching the metal sphere here. And again, because these electrons don't like to be near each other and they're sort of all stuck together on this rod, as soon as I touch this rod to the sphere, these electrons are transferred onto the sphere and they're going to spread out because, again, they still don't like to be near each other, so they're going to move on this sphere in a way that they're spread out. The reason that they don't move off of this sphere is because this is an insulator, the stand. So that doesn't conduct, it doesn't allow those electrons to continue to move. If this was a conductor instead, these electrons would move off of here and go to the ground. Label the right-hand sphere below with the appropriate charges below for a positively charged rod touching a metal sphere. So it doesn't matter whether the charges are negative or positive, like charges repel. That means that they don't want to be near each other. So as soon as this positively charged rod touches this metal sphere, these positive charges are going to move onto that sphere. And again, because positive charges don't like to be near each other, they're going to go ahead and spread themselves out all over that sphere. So again, this is charging by contact because that rod actually touches that sphere and allows those positively charged particles onto this sphere. And again, they spread out because like charges repel, so they're going to move away from each other as much as possible once they're on that sphere. Again, they stay where they are because this base here is an insulator, and so it doesn't allow those positive charges to continue to move. In the examples above, electric charge is simply transferred from one body to another. Okay, so again, we had the electric charge move from this positively charged rod onto our metal sphere, and we had our negative charge move from this negatively charged rod onto this sphere. So the charge is just transferred from one body to another. A positively charged balloon will stick to a wooden ball. It does this by polarizing molecules in the wooden wall to create an oppositely charged surface. So a couple things here. A positively charged balloon, right? So that means this balloon is positively charged. Again, those positive charges are going to be spread out over that balloon because like charges repel. So there's our positively charged balloon. It does this, it's sticking to this wall by polarizing the molecules in the wooden wall to create an oppositely charged surface. So this is causing, okay, a charge here. And so this area of the wall that is near the balloon is going to be negatively charged. Why is it negatively charged? Because we know that opposite charges attract. So if this balloon is sticking to the wall, it's doing so because this wall is polarized. The particles that make it up are polarized so that the negative side of those molecules is towards this balloon, which is attracting the balloon to the wall. Now, these particles, though, still have positive charge in them as well, but again, those positive charges are going to be away from this balloon. And so these positive charges are over here. So we completed this diagram. And again, remember, these moved away because like charges repel. So because this balloon is positively charged, the positive side of these molecules of wood are trying to get as far away from this balloon as possible. Consider the diagrams below. In picture A, a pair of insulated metal spheres, A and B, touch each other, so in effect they form a single uncharged conductor. So again, our balls here, okay, these are conductors, these are our spheres, and again, this part is an insulator so that the charge can't move off of these metal spheres. Now we're moving on to picture B. A positively charged rod is brought near A, but not touching, and electrons in the metal sphere are attracted toward the rod. Charges in the spheres have redistributed, and the negative charge is labeled. Draw the appropriate plus signs, positive signs, that are repelled to the far side of B. Draw the signs of charge. Okay, so there's what we're supposed to do, right? So this time, right, we have our positively charged rod. So again, kind of like that balloon did with the wall, right? But here it's not just polarizing the molecules, it's pulling the negative, right? This was neutrally charged, so there were both positive and negative charges on these spheres. But by bringing this rod in here, it means that the negative charges on these two spheres is going to move towards this positively charged rod because, again, opposites attract. Okay, so our opposite charges attract. Now, not only remember do opposite charges attract, but like charges repel. So where are these positive charges going to be? They're going to be as far away from this rod as possible. And we have 5 of them drawn there, so we'll do 5, 2, 3, 4, 5, right? They're going to be as far away from this rod as they can get. So they're going to be on sphere B and as far away as possible. All right, now we're moving on to C. Draw the signs of charge in C when the spheres are separated while the rod is still present. So what that means is these charges are still going to be the way they were. Okay, when we separate them. And in D, after the rod has been removed. Now, the rod's not here anymore, right? So there is no kind of force of attraction or repulsion here. So, first off, the positive and negative charges are going to kind of spread out a little bit. But now remember, this sphere has a negative charge, and this sphere has a positive charge. And what do we know about opposite charges? They attract. So, this negative charge is going to be attracted to the positive charge of B. So the negative charges are kind of along this surface of A, and the positive charges are along this surface of B because opposite charges attract. So now we're going to look at a similar thing, but now we're going to have a negative rod. So consider below a single metal insulated sphere, okay, initially uncharged, right? Uncharged means, right, we have a balance of positive and negative charges on this sphere. And again, this is an insulator, so the charges can't get off of our metal sphere. When a negatively charged rod is nearby, as in picture B, charges in the metal are separated. Electrons are repelled to the far side. So we bring this negatively charged rod. Again, opposite charges attract, so the positive charges that were on that sphere are going to be close to the rod, and the negative charges that were on that sphere are going to move away from the rod. Okay? So they're sort of separated. Have positive on this side because of that attraction, and negative on the far side because of that repulsion. When the sphere is touched with your finger in picture C, electrons flow out to the sphere to earth through the hand. The sphere is grounded. So what happens here is, as soon as I touch this, because I'm touching the ground, I provide a way for those electrons to escape. Why do they escape? Because again, they're still repelled by this negatively charged rod. They're trying to get as far away from that as they can. Well, now they have a way to do that. So that negative charge is moving through me, right? The arm here is acting as a conductor, right? Because this is still my insulator. Okay, but the arm and the hand are acting as a conductor, and they're conducting or allowing those electrons to move off of this sphere and to the ground. Note the positive charge left in picture D, while the rod is still present and your finger removed. So basically, again, what's happened is the negative charge from the sphere is gone. It's left. It was transferred through the person's body that touched this to the ground. And E, when the rod is removed. So what's the difference between this and this? Well, now there's no rod here, so there's no attractive force. So now these like charges are repelling each other, and they're moving as far apart as they can. So they spread out over that sphere. So now we're going to look at the same type of thing, but with negative charge, with a positively charged rod. So the diagrams below show a similar procedure with a positive rod. Draw the correct charges in the diagram, right? So there's no charges here shown because they're balanced. They're just all spread out evenly on this sphere. They're not moving because they're stuck on the sphere. So now I bring this positively charged rod in. So this time it's going to be the electrons that are attracted to it, okay, the negative charge, and the positive charge is going to be repelled to the other side of that sphere, right? So we have kind of a negative here because there's that attractive force, and the positives over here because there's that repulsive force. So again here, we still have the negative charge attracted to that sphere, but we have touched it. So what has happened? These positive charges here are moving off of the sphere, down our arm, and to the earth. In this picture then, when somebody isn't touching that sphere anymore, right? Again, our arm was acting as a conductor. Because this rod is still here, these negatively charged particles are attracted to that rod. But there are no more positive charges on here because they all escaped that sphere to the ground. And then finally, when we take this rod away, these negative charges, they don't really like to be near each other. They're only near each other here because they're attracted to this positively charged rod. So now they're going to spread apart. So that's what that diagram looks like. So I hope this has helped you understand how like charges repel each other and opposite charges attract each other, and how this works in metal spheres and even in the wall. Thank you. Have a great day. I'll talk to you tomorrow.